So section 2 starts to get into the actual integrals, and we're going to ease our way into this. All right, so the first thing you want to remember, so our Riemann sums really are just an indication of our summation. Remember, this is the Greek symbol for sums. Okay, sigma stands for sum. We just really found each individual area and added them all up. That's going to lead us into this next part. Oh, and somewhere I must have left off the theorem 1 just says that, I don't know where it went. It just says all continuous functions are integrable. So theorem 1, let me just make sure it's not on the next. Oh, it is. Okay. You can actually leave this definition off. I'm just going to let me just talk through it a little bit. So if we have a function, we have this graph all the way through. We've been talking about determining area between the curve and the x-axis. So we're now going to combine the word integral as a limit of Riemann sums. All right, so when we're looking at our interval from A to B, we're going to start from A and go all the way to B. What the integral ends up being, remember how we kept talking about dividing up into intervals? And we want to make as many intervals as we can. The more the intervals you make, the more accurate it's going to be. Well, what we're going to do is we're going to actually take the limit and the number of partitions we're going to send to 0. And what that ends up doing is we're going to, that'll lead us, first of all, let's talk about theorem 1. All continuous functions are integrable. If a function is continuous, you can find its integral. All right, so that's really important, but it ends up just making sense. So just like we want to take our partitions, we're going to partition into n subintervals of equal length. Remember how we found our width? It was just the change in x. So b minus a divided by the number of partitions n subintervals. Does it make sense that if we send n to infinity, we're finding as many, we're in that interval, we're finding as many sums as possible and adding it all up? And so the integral is just sending the number of partitions to infinity, that we take every single possible number of partitions, okay? All right, so this still doesn't quite make sense, so don't freak out yet. All right, so Greek versus Roman. Let me... So we're used to the summation, and we're going to take the limit as n approaches infinity. What we're going to do is make it a little bit more easier to understand. And where this is the Greek symbol, the Roman symbol for sum is this elongated S. All right, this elongated S is the integral sign. The integral is just your antiderivative, the inverse of derivatives. So when you see this symbol, it's just the inverse of the derivative. This A and B, that goes directly from your interval. We're going from A to B. So this is the start, and this is the end. this is the actual function. Notice where the delta x, the change in x, we literally just change it from the Greek delta to the English d for delta, dx. And think about differential when we moved our dx to the other side. That's really another connection there. And this is showing you the variable that we're integrating with respect to. Okay. Now, this is really important here. Whatever variable is being used, it doesn't matter. As long as these two match, you can use any variable you want. It's just really a dummy variable. So don't let that throw you off. All right. So this is just changing it from the Greek into the Roman. We're not even doing any calculations. We're just switching it over from the Greek to the Roman. And the Roman is so much easier to simplify. It's just so much better. Now, the first thing you have to understand, you got to plug in your interval from -1 to 3 on that elongated S. You're just going to, since this is delta x, this is showing us we're just going to use x. So we just replace each of them with the x variable. And changing our delta x into dx. That's it. Greek into Roman, done. Okay, so the definition's important. The area, notice I have a start. The area under a curve as a definite integral. They really want you to connect area and integral, okay? If y equals f of x, first of all, non-negative and integrable over a closed interval from a to b, then the area under the curve, the area equals the integral. The area equals the integral if it is non-negative. That's really important because we'll talk about that in just a minute. The area equals the integral for non-negative functions. Okay, so there are times that we can use area to help us find the integral value. So we're going to learn how to find we've talked about antiderivatives, but this is not one we want to use an antiderivative for. So we're going to use area. So first of all, what does the square root of 4 minus x squared, what is that as a graph? All right, I don't know if this will help some of you. If we square both sides and y squared equals 4 minus x squared, move the x squared over, x squared plus y squared equals 4. This is the entire formula for the circle. All right, and this is where the radius, a circle with radius 2. So 2, radius 2 would be the whole circle. That would be this formula. But notice they just have the square root of 4 minus x squared. Do you remember what that means? That's really just the top half of the circle. Because remember how we talked about area equals the interval only for non-negative functions? So what we're going to do is calculate the area between the curve and the x-axis. Let me erase a little here. So first of all, what is the area of a circle? Is pi r squared. So if the radius is 2, the area of the entire circle is 4 pi. But notice, I just want the top half of the circle. Look at the interval. This interval is very important. -2 to 2. I'm just looking at it from here to here, which ends up being half a circle. So what I'm going to say, I'm going to erase this part. This integral value, evaluate the integral, is just 1/2 4 pi, which is 2 pi. So if you can graph the function, and if you know the formula of the area of that function, you can use area to find the integral value. Okay, so let's consider this part. This is really, really important. So what we just talked about was for non-negative functions, but we know there's going to be graphs that's below the x-axis. We have tons of that everywhere, right? So this is important here, is the integral value. If the function is below the x-axis, will be negative. So if we're evaluating something that falls below, it's just going to be negative. Now, what's super, super important here, area itself cannot be negative. We never have a negative area, but the integral value can be negative. So let's think about that. That means that area, if the function is below the x-axis, if the function is negative, that means the integral is negative. We have to do the opposite of the integral value to find the area. Because if this is negative, we just need to make it positive to find the area. So we're going to be going back and forth between area and integrals and area. We can help find the area by using integrals, and we can find integrals using area. Okay, so typically we're going to have areas that are both above and below the x-axis. So to find the integral value, the integral area, because it's positive above and negative below, we'll just take the area above and subtract the area below. We're going to find each area, and the above will be positive, the below will be negative, and the integral will be the combination. Okay, so this is just an exploration using the sine curve. All right, so if we consider this equation, we know the sine curve from 0 to 2 pi looks like this. And what this is saying is the area from 0 to pi, the integral value is 2. So use what you know about integrals and area and the curve to determine the values. All right. So what this is saying is if the area from 0 to pi is 2, number 1 is saying what is the integral value from pi to 2 pi? Well, does it make sense? This area would be the same as this area. So that means this is 2, This is 2. The area of both regions is 2. But the integral value from 0 to pi, because it's above the curve, above the x-axis, is a positive 2. The area from pi to 2 pi is below the x-axis, so it's a negative 2. All right, how about between 0 and 2 pi? Well, if this is a positive 2 and this is a negative 2, the integral value would be 0. Number 3, going from 0 to pi over 2. Well, if the whole curve above is positive 2, what would halfway across be? Positive 1. Number 4. This one gets a little bit more interesting. Let's graph this out. What does it mean if I add 2 to the original sine function? What that's going to do is lift the sine curve up 2 and still have that hump going from 0 to pi. So this hump here is still the same as this, so that's your 2. And then what's going to be the area of this rectangle? Well, we know this is 2, this is pi, so does it make sense? This rectangle has an area of 2 pi. So if I want to look at this whole shape here, I get 2 plus 2 pi. All right, number 5. What do you think we're going to do if we take 2 times the curve? We're just going to take 2 times the original area to get 4. All right. Number 6. All right, so this one's a little bit stranger. This is shifting everything to the right 2. So does it make sense if I'm shifting everything to the right 2? Notice this went from 0 to 2. This went to pi plus 2. Everything shifted by 2. Everything was translated, so it's going to keep the original area value of 2. All right, number 7, we want to extend this out. So this is from 0 to pi, and this would be back to negative pi. So I'm going to have the same amount of area below as I do above. So that's also going to be a value of 0. All right. And number 8, what does this do? X over 2. So let's think about this. This changes the period. All right. Our original period is 2 pi. And if I do my 2 pi divided by my k value, it's now 4 pi. So my original period of 2 pi, because it's x over 2, we got to adjust our period. So now, instead of this going to 2 pi, because of the 1/2, it's now going to 4 pi. So now 0 to 2 pi is still the same. Okay. So we're shifting this out. All right. This is just a constant function. So every time that we take the integral of a constant, if the function we're taking the integral value of is a constant, let's think about this. If we look at the visual here, if we graph a constant, just like we graphed the velocity function back in the beginning of section 1, a constant c is just a horizontal line going from A to B. It just ends up being the area of a rectangle. So c is our width, b minus a is the length from A to B, and we can just plug it into that value. So this is the exact problem I was just talking about. If we want to revisit the ship problem, we've talked about what this looks like. 7.5 would be a constant value from 7 to 9. Now, it says express its total distance traveled as an integral. So we want an integral. And how would we list the start time? From 7 to the end time, 9, of the function 7.5 dt, then evaluate using the previous theorem you just wrote down. So that's where we take c, 7.5, times b minus a, and we still get our 15 nautical miles. So the accumulator function. Okay, so let's go ahead and graph 1 plus 2t. If we think of this on a graph, this is just a line up 1 with the slope up 2 over 1. So this is the equation, the graph of that equation of a line. And we want to go from 1, and notice this point here, that's 1, 3. We're going to go up till that we get to some x value. So if we draw this coordinate point would be x, and 1 plus 2x would be the y coordinate. All right, so would you agree this shape is a trapezoid? So our area of the trapezoid is our height over 2 times base 1 plus base 2. The height is the distance between the parallel sides. So this is where we just take x minus 1. Base 1 is the height here, which is just our y value, 3. Base 2 is this height, or this y value. So the area of this specific trapezoid is h over 2 times the quantity, base 1, which is 3, plus base 2. Let's go ahead and I'm just going to do this. I can combine my like terms. I can see that I could factor out a 2 here and cancel this 2 out. And then I can distribute. And I'm just going to put it in descending order. So x times x squared, then I get negative 1x plus 2x is plus x minus 2. And that's what we call our accumulator function. Okay. Okay. So whenever you see the denoted something as nint, it's just your calculator. And where the derivative was all about math 8, nint is math 9. So if you get your calculator out and push math 9, you're literally going to see this and you're just going to fill in the stuff. So if we do that for example 5, go ahead and do math 9. You plug -1 in for the bottom number, +2 for the top number. Make sure your mode is always in radians, since we have our trig function. Then take your x times sine of x, and then fill in the x variable for the dx. And if you just plug all that into your calculator, I must have just copied these numbers down from the book, because I only have 2 decimal values. You always want to go 4. So I would write down the 4 decimals. Okay. Letter B, same thing. Going from 0 to 1, I would use your fraction bar, so you don't need to worry about order of operations in parentheses. Remember, that's the green alpha y equals gives you all of your fraction bars. And you'll notice this ends up being pi. What this has to do with is this ends up being your tan inverse function. So just a little FYI. And be really careful. Make sure this negative is you're using your negative button, not the minus sign. Otherwise, it's going to cause you some problems. So those should be the values when using your math 9 for example number 5. Oh, one thing I'll point out, this used to be what you'd get for NINT, and since they upgraded the operating system, it's so much nicer because it actually looks like your integral. All right, last one. So we've talked about how all continuous functions are integrable. Theorem 1 guarantees it. But there are some that can be integrable, able to be integrated. Okay, so let's consider example 6. Now, this is a function that we've seen multiple times, and you might not remember exactly what this graph looks like. But if you plug in -1, I plug -1 in for each x, I get a +1 on top and a -1 on bottom. That's -1. It wouldn't matter if I plug in a -2 into both of them. I'm still going to get +2 divided by -2. The left side of this is just -1. There is a hole at 0. Actually, there's a jump. Because what happens as soon as I plug a +1 in, +1 over a +1, that ends up being +1 here. There's a discontinuity. There's actually a jump discontinuity at x equals 0. But we can still connect the function itself to the x-axis, and I can find the area. So this is an instance where I would have no idea how to find the antiderivative of that, but I can use area to find its answer. Now, the area of this is 1 by 1, and because it's the area is a +1, but the integral value is negative because it's below the x-axis. Here, this is 2 by 1, so the area is a +2, and because it's above the x-axis, the integral value is a +2. Because we are finding the integral value, I need to do the positive, I need to subtract the negative and add the positive, and my overall value is 1. So a lot of times when we have confusing functions, we can consider the graph and find the area of the graph itself to help us find the integral values.